Problem number 1. A card on the horizontal surface is attached to a spring. The other end of the spring is attached to a wall. The card is initially held at rest, as shown in figure 1. When the card is released, the system consisting of the card and spring oscillates between the position plus L and minus L. Figure 2 shows the kinetic energy of the card spring system as a function of potential energy. Frictional force are negligible. On the graph of kinetic energy, K versus potential energy U, shown in figure 2, the value for the x-intercept and y-intercept are the same. Briefly explain why this is true using physics principle. This is a K versus U, and the x-intercept, that's 1, kinetic energy 0. You have a potential energy 4. Y-intercept means when potential energy is 0, you have a kinetic energy 4 joules. These are the same because mechanical energy conservation. Mechanical energy is conserved. Why mechanical energy is conserved? Once you release this, there's no external force, no work done by the external force. And kinetic energy plus potential energy should be constant. And this value is just a 4. So actually K plus U equals 4. That's the equation for this line. Part B, when a card is at plus L and momentarily at rest, a block is dropped onto the card. And the blocks stick to the card, and the block card spring system continues to oscillate between minus L and plus L. The masses of the card and the blocks are m0 and 3m0. Frequency of the oscillation before the block is dropped onto the card is f1. The frequency of oscillation after block is dropped onto the card is f2. Calculate the numeric value for the ratio f2 over f1. Okay, so we know the f is related to the period, right? F is 1 over period. So on the formula sheet, you probably can see the period is 2 pi times m square root m over k. So for f1 is related to t1. t1 is 2 pi square root m naught over k. At t2, when this 3m naught stick to the m naught, then the mass will be 4m naught. So the period is going to be like this. And if we want to find the frequency f2 over f1, that is exactly t1 over t2 because frequency and period, they are inversely proportional. So t1 to t2 is, if we look at this expression, you can find, let's do this way. So you can first cancel the 2 pi, and you can also cancel the m naught k. So we have a square root, so the top, so if you divide bottom by square root m naught over k, the top would be 1, the bottom is square root 4, which is 1 over 2. So that's the numerical value for the ratio f2 over f1. Problem 2. Students conduct an experiment to determine the acceleration of the card. The card is released from rest at the top of the ramp at time t equals 0 and moves down the ramp. The x-axis is defined to be parallel to the ramp with its origin at the top. The students collect the data shown in the following table. Which quantity could be graphed to yield a straight line whose slope could be used to determine the acceleration of the cart? So we want to find the acceleration from a straight line, and we have a data position versus time. So first we should write the kinematic equation that relates position with time, right? So that equation shows x is x naught plus v naught t plus 1/2 a t squared, right? So initial position is 0, so we don't have to write that. And initial velocity v naught is also 0 because start from rest. So the position is just 1/2 a t squared. Now if we can graph x versus t squared, the slope is just 1/2 a. Okay, we're going to find the slope first and multiply slope by 2, then we can find a. So we need x versus t squared. So we should put t squared here, which is second squared. And we need to use calculator to get these values. So first one, 0.039 squared. That's 0.152. 0.59 squared. That's 0.348. 0.77 squared. It's 0.593. 0.96 squared. That's 0.922. 1.2 squared, that's 1.44. Okay, so the vertical axis should be x. Horizontal axis should be t squared. On the following grid, plot the appropriate quantity to create graph that can be used to determine the acceleration. So we're going to plot the data and get the best fit line. For the vertical axis, we need to get the position, which is the meters. Horizontal axis, that's a t squared, which is second squared. And from our data, so the position is from 0 to 0.55. So I would say 0.1, 2, 3, 4, 5. That's good. So this is 0, 0.1, 0.2, 0.3, 0.4, 0.5. And for t squared, it's going from 0 to 1.44. See, this is 0.24681, 1.2, 1.4. That's good. So here is 0.2, 0.4. Let's just use 2 sig figs. 0.4, 0.6, 0.8, 1.00, it's 1.20, 1.40, and so first one we need 0.06, 0.152, 0.06, 0.152. So 0.152 is about here. 0.06. So it's about here. The second one, 0.14, 0.348. It's about here. Third one is 0.24, 0.593, 0.24, here 0.59, let's say it's around here. And next one, 0.37, 0.922. It's about here. And next one, 0.55, 1.44. So 1.44 is around here, and 0.55, 0.55 is around here. So this is the position. So we gotta draw a best fit line. A best fit line. Okay, let's say this is close to the best fit line, and we got to pick up 2 points. So let's pick up 2 easy points. This point looks like a pretty good point, and next one probably here. So the slope is gonna be the change of the x. This is 0.58, 0.58 minus this one is 0.1. So the difference of t squared, that is 1.5 minus this is 0.25. So we can, this is 0.48 divided by 1.25. So we have a 0.384 for the slope. And we know slope equal to 1/2 a. So a is 2 times 0.348. That is 0.768. So it's about 0.77 meter per second square. Use the line you drew in part A2, calculate the experimental value for the acceleration. Okay, this is what we just did. Part B, the students are asked to determine the experimental value for the acceleration due to gravity G experiment using their data. What additional quantity do the students need to measure in order to calculate G from A? To get the experiment G from A, we probably need to use Newton's law to derive A in terms of G. So we can first draw the free body diagram. Suppose this is the ramp. We have a cart. So there is a gravitational force acting on the cart, and there is also normal force, and the perpendicular component of the gravitational force is balanced by the normal force, and there is a parallel component left. So if we don't consider the friction force, then the net force is just the parallel component, which is mg sine theta. So this is ma according to Newton's second law. Then a is g times sine theta. You can also express g in terms of a. G is a over sine theta. This g is experiment G. So if we want to get G experiment, we need to measure the theta. So So the theta is need to be measured. So this theta, you can see angle between ramp and horizontal. Write the expression for the value of G experiment in terms of A. So we already got this. Part C. The students calculate the value of G experiment to be significantly lower than the accepted value of 9.8 meter per second square. What is a physical reason other than friction or air resistance that could lead to a significant difference in the experimentally determined value of G experiment? So other than friction, or if there's a friction force, definitely can make the acceleration smaller, but other reason that could be the A might be wrong, or the value of A might be wrong. So for example, the measured time T is not correct. So we can say measured time is significantly longer than actual time. So, number 2, briefly explain how the physical reason you identified in part C1 would lead to the decrease in experimentally determined value G experiment. You can say if measured time is significantly longer than the actual time, then the A should be significantly smaller than the actual A. If A is significantly smaller than actual A, then the G, because the G is A over sine theta, so G can be significantly smaller than expected. Another reason could be the theta could be wrong. Theta could be wrong, but I think theta is easier to, this angle is easier to measure. It's not likely to be significantly larger or smaller than the actual one. But the time, if you use a stopwatch, it might be hard to control the time. If your reaction time is too long, the measured time can be significantly longer than the actual time. Part D. The students want to confirm that the acceleration is the same whether the cart rolls up or down the ramp. The students start the cart at the bottom and give the cart a quick push so that it rolls up the ramp and momentarily comes to rest. The x-axis is still defined to be parallel to the ramp with the origin at the top. On the following graph, sketch the position x and velocity v as a function of time that correspond to a scenario shown while the cart moves up the ramp. We want to get x versus t. So according kinematic equation, it's going to be a quadratic function. So the x is x naught plus v naught t plus 1/2 at squared. And if this acceleration is constant, then the x versus t should be a parabola. And since a direction of a is down, it's same direction as positive x, then this parabola should be opened up. The initial position here is x that's positive x. So if you start from here and going down, so this x is decreasing, but the cart is going up. When the cart gets to the highest position is going to slide down, so the x going to increase. For v versus t, if x versus t is parabola, v versus t would be a straight line. So the initial v is in the negative x direction. That's negative value. When it gets to the highest position, it's going to be 0, and then sliding down, it's going to become positive. So the v would be like something like this. That's the end of the problem. Alright, number 3. A small block mass m0 is attached to the end of a spring constant k0 that is attached to the rod on the horizontal table. We have a rod. A rod is attached to the motor, so the rod can rotate at various speed. So the rod can rotate about its axle, and so when the rod is rotate, this block spring system gonna also rotate doing a circular motion. And when the rod is not rotating, the block is at rest and spring is at its unstretched length L. All friction forces are negligible. At time t is t1, the rod is spinning such that the blocks move in a circular path with constant tangential speed v1, and the spring is stretched a distance d1 from the spring's unstretched length. At time t2, the rod is spinning such that blocks move in a circular path with constant tangential speed v2, and the spring is stretched a distance d2 from the spring's unstretched length. d2 is greater than d1. So basically, when the rod is rotating about its central axis, the block is doing a circular motion. On the following dot, which represents block at location in Figure 1 and Figure 2, draw the force that exerted on block by the spring at time t1, t2. So we got to draw the force acting on the block for these two scenarios. For this one, since this is doing a circular motion with constant speed, then the only force, net force acting on the block should be the centripetal force. Centripetal force is provided by the spring. The spring force is the centripetal force, and this one is same, but for T2, since the spring is stretched longer, the force, spring force, should be greater. The centripetal force is also greater. So when we draw the force, it should be toward the center, which is to right. For T1, you gotta draw a vector, draw arrow which is smaller. This one, you draw arrow that is greater. Okay, number 2, referencing D1 and D2, describe your reasoning for drawing the arrows the length that you did in part A1. So the reasoning is that for T1, the stretch of the spring, D1, is smaller than D2. D2 is the stretch of a spring at T2. So if the stretch of a spring is smaller, then the force, spring force, should be smaller. So the reasoning, stretch of spring is smaller at T1 than T2. Three is the tangential speed v1 of the block at time t equals t1 greater than, less than, or equal to the tangential speed v2 of the block at time t2. Tangential speed is related to centripetal force, right? the centripetal force is greater for T2 than T1, then, so let's write this centripetal force Fc is mv squared over r. Okay, so for Fc, that's just the spring force. Spring force is related to the stretch, the amount of stretch. For T1, the stretch is D1, T2, the stretch is D2, but the radius, this radius is D1 plus L, this radius is D2 plus L. So let's rewrite this equation for T1 and T2 at T equals T1. So the spring force is going to be K times D1, which is mv1 squared D1 plus L. So you can rewrite V1 squared as K D1 times D1 plus L divided by M. At T equals T2, so the spring force is K times D2, that is M V2 squared over D2 plus L. So V2 squared is K D2 plus L over M. So compare V1 and V2. If you look at the difference is this. So D1 is smaller than D2. So D1 plus L is also smaller than D2 plus L. So when they multiply together, it causes V2. V2 squared is greater than V1 squared. Thus V2 is greater than V1. So V1 is smaller than V2. You should choose this one. Question B. Consider a scenario where the block travels a circular path with where the spring is stretched the distance d from its unstretched length L. Determine an expression for the magnitude of net force F net exerted on block. Express your answer in terms of M naught, K naught, L, D, and the fundamental constant. When a block travels on a circular path with constant speed, the net force must be the centripetal force. The net force we can write as net force is just the spring force, is K naught times D. Because for the block, the gravitational force and the normal force should be balanced. So the only unbalanced force is just the spring force. So the net force is just the spring force. B2, derive the equation for the tangential speed v of the block. Express the answer in terms of M naught, K naught, L, D, and fundamental constants. So this is something we just did. Let's do this one more time. So tangential speed is related to the centripetal force. So centripetal force is this K naught times D, and that is M V squared over R. So we should express R in terms of D plus L. Now the V is, we need to multiply K naught D by D plus L, and then divide by M. This is V squared. So V is just the square root of this. So V is square root of this term. Does your equation for the tangential speed of block from part B agree with your reasoning part A? Yes. So the reasoning. Okay, so I think we should say a little bit about the reasoning. Yeah, so the reasoning is this expression. So V is related to D, right? The bigger from this expression, the bigger the D, the bigger the top, and thus the bigger the inside radical. So after taking the square root, the V should also be bigger. That's I think that's the reasoning. Number 4, we have a block of unknown mass. It's attached to a long, lightweight string that is wrapped several turns around the pulley. This is pulley mounted on a horizontal axis through its center. The pulley is uniform disk with mass m, and the rotational inertia of the pulley is this. The pulley can rotate about its center with negligible friction. The string does not slip on the pulley as the block falls. When a block is released from rest, and as the block travels towards the ground, the magnitude of tension exerted on the block by the spring is Ft. So we know there's a tension Ft acting here. Now, determine the expression for the magnitude of angular acceleration alpha d of the disk as the block travels downward. Express your answer in terms of m, r, Ft, and the physical constant as appropriate. We want to find the magnitude of acceleration of the disk. So angular acceleration is determined by what? Determined by the torque, right? By the Newton's law for rotation. We have a net torque equals I times angular acceleration. I is already given here, and we need to find net torque. So we have to look at how many forces acting on the disk. Of course, there's a gravitational force. It passing through the center, and there's a supporting force by the bracket here, so it's upward force. It also passing through the center. So these two forces passing through the axis of the pulley, so it does not create any torque for the rotation. And we look at there's only this tension left, right? This tension force is definitely create a torque. The torque can be expressed like Ft times the level arm. Level arm is this, that's exactly r, since this is perpendicular. So the net torque is going to be just Ft times the r, which is I is 1/2 m r squared times alpha d. Alpha d is, so we can use this divided by the I, so Ft r over 1/2 m r squared. We can simplify this expression, so cancel the r. We can bring the 2 to the top, which is 2 times Ft over m r. That's it. Next, look at 4b. We have two scenarios. Scenario 1, we have this is same as before, a solid disk. Solid disk, we have a Fa, so pulling, the tension is Fa, pulling down. And scenario 2, we have instead of a solid disk, we have a hoop. So most of the mass is concentrated on the rim. So the mass of the hoop is the same as the mass of the disk. And also we have Fa is pulling down. So the configuration is very similar. The only difference is they have a different I, right? For this hoop, definitely I is bigger because they have the same mass. The average distance from any point to any point on the hoop to the center is longer than the average distance from any point to the center on the solid disk. So this one definitely have a bigger I. So we can say this one has I2, this one I1. I2 is bigger than I1. Okay, so each pulley is free to rotate about its center with negligible friction, and the pulley began at rest. Then both strings are pulled with the same constant force Fa for the same time interval delta t, causing the pulley to rotate without string slipping, rolling without slipping. After time interval delta t, the change in angular momentum of disk is equal to the change in angular momentum of the hoop. So they have a same angular momentum change, same delta L. Delta L1 is same as, so delta L1 is same as delta L2. And but the change in rotational kinetic energy for the disk is greater than that of the hoop. Okay, different change in rotational kinetic energy. So question B is, consider scenario 1 and 2 at the end of the time interval delta t in a clear, coherent paragraph length response that may also contain equation and drawings. Explain why the change in angular momentum of both pulleys is the same, but change in rotational kinetic energy is greater for the disk. Okay, first I want to explain why the change in angular momentum of both pulleys is the same. Angular momentum change is related to, let's say, angular impulse, right? Angular impulse, you can use torque times delta t. That's angular impulse, which is change of angular momentum. So these two, they both have the same torque because Fa is same and the same radius. So, and also the same time interval. On the left side, they are equal, so the delta L should be same. But why is there a difference in the change in rotational kinetic energy? So we have to look at the formula for rotational kinetic energy. So K rotational, that is 1/2 I omega square. So I and omega L. So what is the expression for L? L is I times omega, right? So since they both have the same L, then I would say I1 omega 1 is I2 omega 2. And for rotational kinetic energy, that is, we can rewrite this expression as 1/2 I omega times omega. So this is the same for both scenario 1 and scenario 2. And the difference, whoever has a greater omega should have a greater kinetic energy. So who has a greater omega? Let's look at this one. So since we know I2 is greater than I1, and these two are equal, that means omega 2 is smaller than omega 1 because omega is inversely proportional to I. So for kinetic energy, this part, our common part, and this one. So for the scenario 2, it has a smaller omega, so the change in kinetic energy of scenario 2 should be smaller than scenario 1. Question number 5. A rod with a sphere attached to the end. The rod, a sphere attached to the end, is connected to a horizontal mounted axle and carefully balanced so that it rests in a position vertically upward from the axle. This is vertically upward. The center mass of the rod sphere system is indicated with this symbol. Here is the center mass of the sphere and the rod system. Sphere is lightly tapped, and the rod sphere system rotates clockwise with negligible friction about axle due to the gravitational force. A student takes video of the rod rotating from vertically upward position to the vertically downward position. Figure 2 shows 5 frames that students selected from the video. These frames are not equally spaced apart in time. So if you take a view, take the video from this side, from the right side, you're going to see video frames like this. So first, this one is going to rotate. So because under the gravitational force, it's going to fall, and the system is going to rotate about the axle, and finally it's going to get to the bottom position. So the first question, use the frame of the video shown in Figure 2 to answer the following question. In which frame is the angular acceleration of the rod sphere system the greatest? Okay, which frame? Angular acceleration of the rod sphere system the greatest. Angular acceleration is related to torque, right? From problem 4, we learned that also. So the net torque is I times angular acceleration. And for these frames, the I would be the same. No change in I. So for torque, which one has the greatest torque? There is only gravitational force acting on the system and creating torque, right? So gravitational force is acting on the center of mass. For this one, it's like that. This is directly down. And gravitational force would be equal for all these 5 frames, but the level arms are different, right? So which frame has a longest level arm? Obviously this one, right? This is level arm is just the length of the rod, a little bit longer than length of the rod, but others are all smaller. Level arm all smaller than that. So we're going to choose frame C. Frame C has greatest angular acceleration because angular acceleration is net torque divided by I. So C has greatest torque because it has greatest lever arm. Okay. A2. In which frame is the rotational kinetic energy of the rod sphere system the greatest? Rotational kinetic energy. So how can the system get rotational kinetic energy? This kinetic energy is actually coming from the potential energy, right? Initially, the system, the center mass is at highest position, right? So when this fall and rotate, the center mass is falling down, it's going down, and as the center mass is going down, the potential energy is changing to kinetic energy. So which one has the greatest kinetic energy? That's the greatest change in potential energy, right? So the potential energy decrease most. That corresponds to the kinetic energy increase most. So this one is at the lowest position. So frame E should have greatest kinetic energy. So frame E. So justify your answer. You should say change of kinetic energy is a negative change of potential energy. So for frame E, the delta U, change of potential energy, is greatest. So it's decreased most, and thus the kinetic energy should increase most for frame E. Part B, The rod sphere system has mass m and a length L. The center mass is located a distance 3/4L from the axle. Derive expression for the change in kinetic energy of rod sphere Earth system from the moment shown in the frame A to the moment shown in frame E. Express your answer in terms of m, L, and the fundamental constant. So we want to find the change in kinetic energy. From part A, we know the change in kinetic energy is negative change of potential energy. This is because mechanical energy is conserved. Change in potential energy is related to change in the height of center mass. So the final position, the center mass is 3/4 L below the axle. For initial position, it was like here. The position is 3/4 L above the axle. So the change in H, delta H, is going to be negative 2 times 3/4L, which is a negative 3/2L. So the height decreased by that much. So the change in potential energy will be negative mg times 3/2L. So the negative sign cancel out. This delta K would be 3/2L mg. Explain why the rod and the sphere gain kinetic energy even if Earth is not included in the system. If Earth is not included in the system, then the gravitational force would be just external force. If this external force does work, then the kinetic energy of the system will be changed. So the work done by the gravity is related to change of the U, right? But we can also express using the definition of work. Work done by the Fg is going to be Fg, which is mg, times the displacement. So the displacement is this 3/2L. So the work done by the gravitational force is positive because the direction of the force and displacement are in the same direction. So since work done by the gravitational force is positive, that's why the rod and sphere gain kinetic energy. That's the end of the problem.